In today's video, we will be working on creating a simple scoring system in assembly language using a couple of different methods. I plan to slow down a bit and try to explain things a little better than I've done in the past. The reason I wanted to work on scoring was twofold: to cover the binary coded decimal system and because I've never actually written my own scoring program in assembly language. This will be my first tutorial utilizing Kick-Assembler. Alright, let's open up Sublime Text. And the first thing we're going to do is create a folder. Call it scoring. And we'll do a new file. BCD1. And the first thing we have to do here, just to get started, is put basic upstart. And this is a Kick-Assembler kind of macro. And we're gonna create a system up here with of bytes that will work as our scoring. I'm going to use 8 bytes. And I'll explain what this is. Alright, before we go too far, let's take a look at the CPU status flags in 6502. These CPU flags are what are used to determine the results of instructions like comparisons, branches, and all sorts of everything that's utilized on the 6502 instruction set. And they are: bit 0 is a carry flag. So you have the carry flag, the 0 flag, the interrupt flag, the decimal flag, break, overflow, and the sign flag. On this example source code I'm working on right here, we're going to be setting or checking 2 of these status flags, and that is the decimal flag and the sign flag or negative flag. The first program I'm working on sets the decimal flag, and the command to set that flag is SED for set decimal. The command to clear it is CLD for clear decimal. So we're going to tab over a little. So when we get ready to use the decimal mode, we'll use the SED command. And what that does is it changes the CPU, the behavior, so that instead of using this essentially hexadecimal, we're now using base 10. So in examples like this, if you were to add for 99, if you were to add 1, it would become 00 in BCD mode. Or if you were to subtract 1 from 0, it would become 99 in BCD mode. Whereas in hex, if you were to do the same thing, it would go to FF. If you were to subtract from 0, it would be FF. Or if you already had FF for 255 and you were to add 1, it would also go to 0. And this has advantages for use in programs like scoring, or just basically doing any kind of floating point arithmetic type operations. It makes it a little easier. It's sort of an outdated system. It's not used very often, but I thought we would cover it here in this example. All right, so the idea for my simple scoring system is you pick an index that you want basically for the digit to add to. You're going to add to one of these numbers, and then whatever digit that you add it to, it's going to carry all the way to the left. So if you have a 99 here and you add 1 to it, that will make this a 96, and then this will be 0, 0. If these were all 99s, then this would become a 0, 1, and then these would be all zeros. So that's how I plan to implement scoring. It's a real simplistic sort of system. So anyway, let's get started. So the first thing we're going to do is we're going to set the carry flag because I plan to do a subtraction. And when you do subtractions, you set the carry. When you do additions, you clear the carry, and the carry being this bit in the CPU flags. Now we're going to load essentially the number of digits. I want the 7th. So how many digits is this? 0, 1, 2, 3. If you're counting from 0, this is the 7th digit. And then I want to subtract an index, because I want to think of it as, instead of, I want to think of it, I'm kind of looking at it backwards. This is position 0, this is 1, this is 2, 3, 4, 5, 6, 7. I wanted to look at it from the reverse point of view. So basically this is your index from the right. And then I'm going to take the result of that subtraction and store and transfer it to the X register so we can use it later. Then we're going to turn on decimal mode, and I'm going to clear the carry because we're going to do an addition. And I'm going to take a number. What I want to do is add 1 to this and see if we can get it to go to 0, and then make this a 96 instead of a 95. So we're going to add 1. We're going to load a number 1. Basically, this is our amount to add. And then we're going to add it to, we need to give a label here. We want to add it to this digit, so I need to give some sort of a label. We'll call it digit. And we also need a label so I can figure out where this is at in memory when we compile this. And so I call that digits. So we're going to add 1 to digit, comma, x, and we're going to store the result at digit, comma, x. And that way, so when we add 1, this should become a 0. But at the same time, we're setting the carry because we flipped over 0. So that should set the carry. We're going to decrease x by 1, and then I need to loop through the rest of them. So I'm going to set a temporary label here for a loop. We could even call it loop. So we're going to load. Now that we've decreased the x register by 1, that means we're looking at this digit. So we're going to load digit, comma, x. Now we're going to add 0 to it. And what that does is if the carry is set, it will actually add 1. If there is no carry, it will add nothing. It will just stay the same. And we're going to store it at digit, comma, x. Then we're going to decrease the x by 1. And then we're going to branch, if positive, branch on plus. That checks the sign flag, and as long as the number is positive, it will branch to that location. Then we're going to clear decimal mode. Oh, we're already doing that down here. And return back. So I got start up here. So the result of this, when we run it, it should be 95, 95, 96, 0, 0. Let's take a look at it. We got error. Oh. Okay, yeah, if you're using temporary labels, you have to do plus or minus, and you have to say loop backwards. We're kind of going up to where the first instance of this loop right here. And you'll notice that our digits start at 80E. So right now we don't have it displaying to the screen, so we're going to look in the monitor. M to look at the digits. 80E. So the first 8 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and you'll see it says 95, 95, 96, 00. So that worked. So I was trying to think of a way where I can improve this a little bit, and what I was going to do is take a copy of it and create another copy here. Call it BCD2. Paste it in. All right, so on this version, I'm going to delete this part. And what I wanted to do was, say we wanted to eliminate this subtraction right here and just use a table instead. What we could do is we could create another table, and we could have something like 7, 6, 5, 4, 3, 2, 1, 0, and then we can use that as our index. And if we did that, we wouldn't need this subtraction. We could do LDY, our index right here. This would be our new index. And then we can say load the X register directly from the reverse table. And then we could eliminate these 3 lines here. And we're only saving a little bit of memory by doing that. Now we could, instead of just hard coding these values like that, we could set a label up here to the number of digits. And that would be 8, so that's how many digits are right here. And we could do a kick directive, a for loop. We can say for I is equal to the number of digits minus 1, while I is greater than or equal to 0, I minus minus, subtract 1 from I, byte I. So that would do the same thing, 7, 6, 5, 4, 3, 2, 1, 0. It might be easier to understand the other way, but this lets the assembler do it for you. Let's see if that compiles. Oops, I see. Oops, this should become a Y. Yeah, I made a mistake right there. Let's try that again. Oops. Digits is still 80E. So yeah, it's still 95, 95, 96, 00, and you can see our table right here, 7, 6, 5, 4, 3, 2, 1, 0. So that's another way of looking at it, and that can even be improved even more. Looking at the program right here, you can kind of see where it's doing a store digit comma x, and then it's decreasing x by 1. Well, that's also happening down here. So why not just jump down to that point and see if it will also still work. So instead of doing this 2 lines, we'll do a jump, and we need to create a label. So we want to jump down to here. And call it skip plus. And then that way we don't need this 2 lines right here, because it ends up doing the same thing. So if you jump down to skip, it ends up doing the same thing. So let's make sure the program still runs. We should see 9595960. Nine five nine five 9600. And we'll do a little more testing on it as we go here. But I wanted to do a few more improvements to it. Now, I'm going to save this one. But I think all this is a little too much. Let's see. I'm going to copy this and do a new one. Call it BCD3. .asm. If you have to do it from the reverse, from 0, then this is 1, this is 2, this is 3, then you might as well just use the index. Why calculate it? Just use it. So just make this 7 if you want to use this. Instead, just think of it backwards. Make that 7, make this 6, make this 5, make this 4. So we're going to get rid of this reverse table. And rather than loading the X register from the reverse table, just set it. Just load it to whatever your index is. Like if you want to look at adding to position 7. So this is still your index of the digit you want to add to. And let's see if that still works. It should work fine. We have our num digits up here. In this example, we don't really need that. So we have 9595 9690. So I think it's just a little cleaner just to set the index. If you just think about it the opposite way, instead of going index 0, 1, 2, 3, just make this 7, 6, 5, 4, 3, 2, 1. We'll save that. So now we have a system that will add to a digit. Now we want to make it so it's a sub. So let's copy this, make a new one. So what I want to do is load the accumulator, load the X register. Right now we have these hard-coded. We're going to create a sub. We're going to call it add to score. And down here where we're loading a 1 and then we're adding digit comma X, we can just take this and move it up here. And then jump subroutine, add to score, and then RTS. I know you can do a JMP if you're going to have a JSR and then an RTS. You could just say jump to add to score and it would do the same thing, but just for simplicity, I'm going to leave it this way. Because you may want to add more. You may want to do more instructions here. So let's make sure this still works. And then this time, let's change it a little. Let's go 99, 99, 99, and see if this 5th digit here gets set to a 1. Just make sure things are working. So So yeah, we have the 5th digit is set to a 1 and with 4 zeros. So that still works. Now we have a quick little subroutine called add to score. So now we're going to want to display it. Instead of looking at the monitor, we're going to want to display the score on the screen. And let's create a new file here. I'm going to copy these. We'll go bcd5 .asm. Oh, let me copy this. Now, to display the score, we're going to need to know the number of digits, how we had that label before. Before we had a label, it just said number of digits is equal to 8. Well, you could hard code it that way, but there's a little trick you can do in the assembler. If you set another label right after all those digits, and I just make an underscore, then you could do a subtraction. Instead of saying 8, you could say, give me the higher number, and then subtract the lower number. So subtract this address from that address, and that'll give you the number of bytes. And let's call it number of digits. And we want to display the score. We'll create a little sub down here. Display score. And on this one, we're gonna need, the way I'm gonna implement it, we're gonna need 2 registers to loop, looping registers. We're gonna load the Y with the number of digits times 2 minus 1. Because if you think of this, there's 16, there's 8 digits, but if you look at each individual nibble and you count each one, then that takes it to 16. So if you count, this is actually 2, 4, 6, 8, 10, 12, 14, 16. And you want to go 0 to 15, so you subtract 1. That's what the minus 1 is, because you're starting from 0. Then from the, so I don't know if I'm explaining this well enough. Let's take our example here and bring it down. Oops. In order to display the score, what we're going to do is we're going to take, starting from the right side, we're going to take that 99 and we're going to look at it in binary. So let's see. We're going to take that 99 and in binary that's 1001, 1001. Oops. And so what we want to do is we want to separate the first 9 from the second 9. And we'll do that by shifting, by using logical shifts to get the first nibble and the second nibble. So let's see, let's start the second part of the loop. The number of digits minus 1. So we want to go 0 to 7 because we're going to count through 0 through 7, but we're going to start at the 7th. And we're going to load digit comma x, so that we're going to load in that 7th byte. Now, since we're doing an operation on it, we're going to need to shift and clear it. We're going to push that byte onto the stack so that we can later pull it back to, so we need to save it somewhere, so we're going to push it to the stack. And what we're going to do, we're going to AND it with 0F. And that's going to clear, that's going to make these 4 bytes here go to 0. And it's going to preserve these 4 on the right. So where it used to be 1001 on the left, it's now going to be 000. So that's what the AND 0F is doing. We're going to clear the carry because we're going to do an addition, and we're going to add 30. You might say, why 30? Well, on the Commodore 64, 30 is the number 0 on the display. So if it's 30, 30 is 00, 31 is number 1, 32 is number 2, etc. Then we're going to store it on the screen, and I'm going to store it on the top left portion of the screen, which is 400. And you notice here we're going to do comma Y. So that's why we have two loops here. One for the display on the screen and one for the digits internally. We're going to decrease Y by 1. So we need that second nibble. So we're going to pull the one that we saved, we're going to restore it by pulling it from the stack. And now, instead of ANDing it with F0, we're going to do the exact opposite. So if we look at that, we're going to AND it with F0 instead of 0F. So if this was 1001, we're now ANDing it on the right side of the nibble. This will be 000. So now we have the nibble on the left side. However, because the nibble is in the it's in the high portion of the nibble, we need to shift it over so it's in the lower portion. So instead of reading 10001, it needs to read 000 1001. It needs to be shifted from the left side over to the right side. And you can accomplish those shiftings by using logical shift. You can either do logical shift right or left, but we're going to use LSR for logical shift right. And you do it 4 times. That shifts it over 4 bits. Then again, we're doing the same thing. We're going to add 30, store it at 400, Y, and then we start our loop. We're going to decrease Y by 1, decrease X, and we need a branch. So we're going to branch if positive, but we want to go all the way up here. Loop minus. And so what we have here, if you look at this, this should display the score in the top left portion of the screen. And the sad part is when you compare it, the display function is more code than addition. Okay, so now we have to remember to call, so it's display underscore score. And let's see if it works. And there you go. Now we have way too many digits here, but this is just an example, but that looks like it's working. So we're going to save it. And we'll get rid of this. All right, so now that we have a simple function that adds to the score and displays the score, I think it's time we added a subtract from score. So let's take a copy of this and do a new one. We'll call it bcd6.asm. And what we're going to want to do is we're going to take a copy of add to score. And I'm going to call it subtract from score. For most of these, instead of doing addition, we're going to be doing subtraction. So instead of clearing the carry, we're going to set the carry. Instead of doing addition, we're going to do subtraction. Put that on the same line here. Except the way you do the subtraction, we're doing this in the wrong way right here. Right here, we're taking the accumulator and we were adding it to digit comma x. What we need to do is instead load the digit comma x. So let's think about this. Copy this down. Actually, let's make this, we're going to do subtraction. So let's make this zeros. And let's make that like 5. So if we subtract 1 here from this digit, then that would make these 9, 9, 9, 9, 4. And let's copy this just so we can reference it. We're going to want to subtract the accumulator from, we're going to load in this digit, this rightmost digit, and we want to subtract what's in the accumulator from that. Subtract some number. So what we're going to do is do a little bit of a self-mod code. Take the subtract value, and we'll store the accumulator right when we come in. It could be right at the top to that subtract value. So that'll be the amount we subtract. So we want to load in the digit comma x, subtract it. And that should do it, but let's make this do subtract from right here and see if that compiles. And that looks right. Let's see, we got how many 9s? 9, 9, 9, 9, 9, 9. Yeah, so 3 9s. 3, 9, 9, 9, 9, 9, 9. So now we have addition, subtraction. Only thing I wanted to do was play around with it a little more. What if we made it all zeros all the way out to here? So now we should have all 9s and then a 2. Let's see if that works. A 0, 2. That's right. And what would happen if you just left it all zeros? What would happen then? So in that case, your carry is over here on the left off the border, but that looks right to me. And okay, so the only thing we haven't really played around with here, let's say we had 55 right here, and we wanted to subtract from that 55. So instead of subtracting from the rightmost, so this would be 7, 6, 5. So we make this 5. And if we wanted to subtract, say, 5 from it, it should be 5 0 0 0 0 0. Yeah, 5 0 0 0 0 0. So what if I wanted to subtract 56? Make it go all the way to negative, so it has to borrow from this side. I'm like, oh, because there's nothing to borrow from. So like if we put a, you know, like a 7 right here, then that should make this a 6 and then a 0 0. Let's see if that works. That's right, 699. That's right, 699. That is the subtraction. The same thing, it works the same way with addition. So now if you wanted to add to 2 different digits, then you would have to call this sub twice. So if you wanted to subtract from, say, this digit and then subtract from this digit. So if you wanted, let's say you're doing 110 instead, add 110 instead of 100, then you'd have to call the sub twice. That's the only downfall of this particular algorithm. Okay, so that's fully implemented using the BCD mode. But what if you didn't want to use BCD mode? What if you wanted to do it in normal mode and see the difference? Well, let's do that. So in that case, I'm just going to copy a little bit of this top part. We'll create a new file. Instead of BCD, we'll call it score1. .asm. And we'll paste in that little bit right there. Now with this mode, instead of everything being 0, you're going to want to start it with 30, because 30 is the hexadecimal version for the number 0, representation of the number 0 on the Commodore. So start everything with a 3. So this would be 0 0 0 0 7 5 0 0 if we were to leave it like that. Without using BCD mode, you're going to want to display all zeros. You need it 0 filled. So we're going to kind of, let's see, let's take the number of digits we have. I should have copied that. We'll take our number of digits, load the X register, number of digits, -1. We'll wrap it around brackets. And we're going to do a loop here. And we'll load digit, comma X, store it onto the screen. Oops, 400, comma X, decrease X, branch, if positive. Well, what we could do is do branch if not equal to 0, and I'll show you what will happen. Loop minus, and for now we'll do an RTS. And let's see if this compiles and runs. Should draw some zeros on the screen. Okay, there we go. Now, you notice it didn't fill in that leftmost digit, and that's because I said branch if not equal to 0. But at that point, so it was equal to, when it hits 0 right here, it breaks out of the loop. That's so by using branch if not equal, it's breaking out of the loop early, 1 byte early. But if we use branch if plus, in other words, branch while we're using positive numbers. So when it hits FF, then it breaks out. So if we use that, then it will hit that leftmost character. So that's a little tip there. That's a little tip and trick to get you to, so you don't have to modify the code. You can actually significantly modify the code. You just change that branch character. Now, if you don't want to write to the screen directly like this, we could use a label. Let's create one called screen. Screen equal to 400. And that way you're writing right to the same address location, but it's in a label at the top. Now, much like before, our X register is going to be the index to this last digit. I'm just going to hard code it for now to 7. And the amount we're going to add, let's make it 1. Start off very simple. So here we have index into digits, digit array, and amount to add. We're going to add, so we're going to do a clear carry. And the first thing we're going to do is add that number 1 to this digit right here. To the rightmost digit, 30. So we're going to do an ADC digit comma X. Now when you add here, we're not in BCD mode, so it's not going to automatically flip from 99 or 39 back to 0. So we have to do a comparison. We're going to compare it to the character right after 39 in hexadecimal is 3A. So we have to compare it to 3A. And if it's less than 3A, you can use a branch if carry clear. That basically is a less than statement. We can do like a skip. We'll need a plus. And so we'll need a label down here for skip. Now, if it's greater than or equal to 3A, then we're going to want to subtract 10. So you subtract 10, set the carry. Oops. Let me scroll down a little. Set the carry. Let me click off of that. There we go. And then we're going to store the value on the screen at position X. So that's where we'll jump to. We'll branch down to here so that if it's less than that, we don't have to do this subtraction. That's all this is doing is skipping this subtraction right here. And then you store it at that position. And then after that, we want to get our next character. So right now we're at this position. So we want to decrease X by 1, so we load in this character. So we're going to decrease X by 1. And we're going to do another loop here. Call it inner loop. Load digit comma X. Add with carry 0 0. And again, if the carry is set, it's going to add 1 to. If it's not set, then it's not going to add anything. But we're going to compare it again. We're going to do the same thing we did earlier. Compare it again to 3A. Branch if the carry is clear to a skip. It's going to do a skip plus. So it's not going to go to the skip up here. It's going to go down to a skip down further in the code. And we'll optimize this, but right now it's going to kind of look like duplicated code. So we're going to subtract 10, set the carry, store the accumulator at screen, comma x, at position x. Decrease x, branch if positive to the inner loop. Minus, because we're going up. So this section right here will hit all the digits. This part right here does the first initial addition of that first digit. And then this loop down here is basically our carry loop. It checks all these digits all the way down, going to the left. And let's see if this compiles actually. What do we got? Okay, I forgot my label. Forgot my label. It needs to be, we're gonna jump. We're just skipping right here. F7. Oh, I forgot my colon. F7. What else did I mess up? Oh, kick is very unforgiving when it comes to case. So like this uppercase L here, it doesn't like that. So now we got 7501. Is that right? I forgot what we were doing here. So we had 7500. We added 1. So now let's make sure the carry is working. If we were to make this 99, so we have 7599. That should make it 7600 if we're adding 1 to that position. So let's F7 and see if that works. 7600. And oops, like we did before, I like to try to carry it all the way down. Let's make this 38. Let's just see what happens. It should be 9 with a bunch of zeros when we run this. Very good. And then if we were to take it all the way and make this a 9, I anticipate all 9s, or is it all zeros? Actually, all zeros? All zeros, because there's no 1 out here on the border. And then, let's see, let's put it back to zeros. Say you wanted to, you had a game and you were making it increment by 100. So, and you're starting off 0. Instead of adding a 1 to this position, you would add it, to this position. Instead of adding a 1 to this position, you would add it to this position. So that's 7, 6, 5. So we would change this to 5. And now when we add 1, it will be 100. When it runs, it should be 100. And it is. So now we can make this a little more efficient. So let's save what we have. Now that it's working, let's save it. And let's make a copy. I think we can optimize it a little bit. Call it score 2. .asm. Oh, and the advantage you see built into this version is it's operating directly on the screen. You don't have to do the math and then copy that to the screen. It's already operating on the screen. But one of the things that we can do is this section right here that I was mentioning is duplicated right here. You see it all right here. So right after this addition, we could do a jump, basically a skip, or let's call it check. And that would eliminate, we don't need this, or this. If we just do that one jump. And the jump that we're going to make it jump down to is the check right here to do this comparison. So just by jumping down to there, we eliminate all that code, and it makes it nice, a lot more clean, I think. And let's make sure that works. Should be 100. And that looks like that worked. Let's make this 9. Let's make it 5 right now, and let's add to position 7. Let's add 1 to position 7, so that should make it 600 when it runs. Let's make sure that works. That's 600. Okay, good. All right, so now that we have that working, we can make a sub to, just like we did before, we can make a sub. So let's do a new file, score3.asm. And I'm basically about right here, add to score, just kind of put a label there, do a jump sub right here. Is that all we need to do? I think it is. Yeah, that's it. Let's make sure that works. Yeah, good, good, good. Save it. And basically the last thing we want to do is do our subtract from score. And to do that, what we'll do is a new file, score4.asm, and we'll just copy the add to score. And instead of add to score, we'll call it sub from score. I like to be able to get it all to fit on one screen if we can. There we go. So now it should be essentially almost the same. We have that same issue though as we had with the binary coded decimal, where we have to subtract the digit first. And we used a self-modify code. We still need to do that here too. So before we do that though, let's change the obvious. We have to, instead of CLC, we're going to do an SEC because we're doing subtractions. Instead of an SEC here down the bottom, we do a CLC. We're kind of reversing it. And then where it does the additions, instead need to become subtractions. Yeah, so this would be like an SBC. and then we reverse them. Instead of subtracting 10, we add 10. So going back to this, we want to load that digit. Oh, let's see, wait. Let's bring this so we can see what we're doing. So think about what we're doing. When you're doing addition, it doesn't matter if you add the accumulator and then add it to the digit here first, or if you load that digit and then add it to the what's in the accumulator. But when you're doing subtraction, the order matters. So right now, what's being passed in is the accumulator. So we want to store that value in the accumulator to a temporary location. And before I called it sub value, subtract value. It's a temporary self-modified code position here. Then we're gonna, since we're gonna do a subtraction, we're doing an SEC. We're gonna load in that digit. I like to think of it as this last digit right here, even though it's indexed by X. And then we're gonna do a subtraction. Subtract sub value. I just put in FF for self-modified code. So what that does is when you store sub value, it's changing this value right here. When you say store sub value, it changes this. So if you're passing in, I'm going to subtract 1. You're going to store it here. This becomes 0, 1. And we're loading in 39. Subtract 1 becomes 38. I'm trying to fit it all here. Oh. This on subtraction, we also have to reverse this. Instead of branch if carry clear, it's branch if carry is set on the subtraction. Okay, now we just got to do a subtraction. Let's make these back to 0, 0. So we have 500 on here. And instead of add to score, we're going to do a subtract from. Did I make that right? Yeah, subtract from. So we're at index number 7 all the way to the end. We're going to subtract 1 from that, so this should be 499 if it runs successfully. Ooh, okay, we got a problem. So as a 3E, it didn't do a subtraction. Maybe you could spot it before me. Ah, wait. Oh, no, that's right. Yeah, subtract. Ah, oh, I see. I see. When you're doing, I should have saw this. When you're doing subtraction, instead of 3A, you're going to compare it to 3.0. Instead of 3A, which is the upper bound, we're going to check the lower bound. And so that's why that wasn't working. So it should be, when it runs, 499. Let's run that again. Yeah, okay. 39. Now that it's working, I'm going to save it. And we'll take out our little cheat here. Anyhow, I prefer the second method to the first. I don't really like using the binary coded decimal system. If we don't absolutely have to use it, I don't see a need to use it. I think this code is a little more succinct. There might be a better way of optimizing this. I'd be interested to know if you guys could shrink the code any better than I was able to do here. I know subtract and add, you could use self-modified code to sort of make this, but there's so many different changes. I thought it's a lot easier to read if it's two separate subroutines. It's a lot easier to read this way than to have one sub with a bunch of self-modified code. It gets ugly that way. So anyway, that's the video. I hope you were able to glean something from it. I will put the source code up on my GitHub. Thanks for watching.